Okay, okay. Fine. हाँ, कर्सर चला जाता है तो कैसे आता है वापस ESC दबा के बाहर आएंगे या फिर बाहर कीजिए? ऐड करके रखते हैं कैसे पासवर्ड नहीं वो पता नहीं एक ये ओके करना है ना कैसे इसको और चला मुझे हाँ ये जो है ना अभी यहाँ से तो मैं मिनिमाइज करके इसको सेट कर देता हूँ हाँ लेकिन जब फॉर स्क्रीन तो दिखता है कर्सर गायब हो गया तो अभी इसको वापस लाने कोई शॉर्टकट नहीं है ऐसा पूरा बाहर निकल के लाना पड़ता है ये तो मुझे पता नहीं ये जूम का प्रॉब्लम है ना ओके जूम से नहीं पता था हाँ ठीक है सो आई डोंट नीड द कर्सर हियर we'll just use the this clicker okay
Thank you for hanging around for the last talk of the day. I know it's late. So our final speaker for the day is Abhishek Sinha. So Abhishek got his PhD from MIT, and after a couple of brief stops, one at Qualcomm and IIT Madras, I think has landed at the right place. And I won't say more because my name also appears on the title. So let him say.
all right Rahul so thanks very thanks for the introduction and for the very kind introduction actually and so welcome everyone so this joint work with Professor Rahul Bhaza at TIFR so the distinction between this talk and the previous few talk is that here in this talk we'll be trying to actually design algorithms, new algorithms that solve some interesting problems. Okay, all right. So this is talking about online optimization. But before we start about what this online optimization means, so what is an optimization problem in general? So in optimization, you are trying to minimize a function. You are given a function f, and you are trying to find a feasible point x, which actually minimizes this function. And if it is a constant optimization problem, in addition to the cost function, say f is known as the cost function, you are also given a constant function. Let's call it gx, and your objective is to find a feasible point, that is a point x star that satisfies a constant g of x, which is less than or equal to 0, and among all the feasible points, it minimizes the objective function. So this is a constant optimization problem, and there are various methods that can be used for solving this problem. But the basic tenet of all this optimization problem is that we are assuming the functions f and g, these are known. Of course, if you don't know the functions, there is no question of optimizing this thing. But things get very interesting when you don't know the functions, right? So of course, so I'm going to qualify this statement. What do you mean by when you don't know the function, but still we are trying to maximize this or minimize this? And not only that, we are trying to satisfy the constants even without knowing them. So we are going to come to that. So this talk is about, this is called the online optimization, and we are going to formulate this problem. It's a sequential optimization problem, and we'll be designing algorithm that solves this sort of problems. Okay, and now this machine learning is all rage. So what is the relationship between the machine learning and optimization? The basic relationship, as I see that here, machine learning is also, it is an optimization problem, but here you are trying to optimize the objective function which you do not know. Okay, what do you mean by that? So we have a loss function. It is parameterized by some parameter theta, and z is your some sample from the data distribution. So what you are interested in? You are interested in minimizing the expected value of this loss function. So you are taking the expectation of this L theta, but the expectation is taken with respect to the data distribution over which you have no idea. You can only have sample access, but you don't know what this data distribution is, right? So it's also an optimization problem, but here you don't know the objective function, the actual objective function. And the question is what you can do in this setting, what kind of guarantees you can actually give by only having sample access to this data distribution. Okay, so there are two paradigms. Okay, the two main theoretical paradigms in which these machine learning problems are studied. The first paradigm is the statistical or the pack learning setting, where you assume that you have got n data points, and they are all sampled IID from some unknown distribution, P data, right? And you design algorithms that that have generalization bounds. And I don't need to explain what generalization means, but this means that this also does well when you have some fresh sample from the same data distribution. So okay, this is a statistical pack learning framework, and lots of work has been done on this setting. There is another line of work that is called the online learning setting, which doesn't assume any data distribution. So in fact, this Z, they actually can be selected in an adversarial fashion, right? And in fact, so we do not make any distributional assumptions on how this data is generated. And you can see that this online learning setting is actually more general than statistical learning setting. In fact, so there is a framework called the online to batch conversion, which says that if you prove any theorem, sort of, this is the meta theorem that I'm going to state. If you prove any like a kind of guarantees for the online learning setting, the same guarantee also extends to the statistical learning setting. So this is the online learning setting is kind of more general, more stronger than the statistical learning setting, and this will be the focus in this talk. Okay. Yes. So this can be okay. So because why I say metal theorem is that I didn't actually qualify what kind of theorems we actually want. So there are various performance metric called the regret, right? And I'm going to talk about that. So any, for example, any bound that is, if you can prove a generalization regret bound in online learning setting, it also gives a generalization bound in the pack learning setting. So this is like a concrete instantiation of this theorem, right? So this is online to batch conversion. Okay, so in this talk we'll be focused on this online learning setting. We'll not be making any distributional assumption on the data. Okay, so any question? So feel free to stop me whenever you have any question or any doubt, any clarification. Okay, so here is a canonical problem that is studied in machine learning. So let's say binary classification. So this is how it works. So you have some model. Let's say you have some model, and this model is parameterized by some weight, and this weight I'll be denoting by this variable called xt. So how it works, on every round, let's say on round t, you get a new sample. And what do you mean by new sample? The new sample comes along with two different things. One is a feature vector, let's call it phi t, and the second is a label. It is a binary classification problem, so the labels could be either 0 and 1. So how does the typical machine learning algorithm work? So this is how it works. So basically, you plug this in, this phi t, the feature vector, to the left, right? And you make a forward pass, and their model gives you some probability output, the probability that this feature vector belongs to class 0 or class 1, right? And then you need to evaluate how well this model actually did. And you actually evaluate this thing with some loss function. It could be a cross entropy loss. Now it takes into account the output of the model and the ground truth, that is the true level of this the feature vector yt. So for example, this loss function could be cross entropy loss, and the important point to remember is that the loss function ft depends on the data point, which is phi t and yt, the feature vector and the ground truth level, and ft is revealed, the loss function is revealed only after the weights are chosen. Right? This might look trivial and this is obvious, but this is important. So you first choose your xt, that's your action, which could be the weights in this setting, and then the loss function, I mean, which could be encoded by the data distribution or the new data point, this is revealed, and this thing goes on in sequential fashion, and the weights are updated, for example, typically by a stochastic gradient descent on FT, on your current loss function, right? So now let me now formalize this thing in the setting of online convex optimization. What I said, I'm just going to formalize this. So what happens is that we have got multiple rounds, and these rounds correspond to roughly the number of data points that you have. So on the first round, you first select an action. This could be the weights in your neural network, and then the environment reveals the loss function F1. Similarly, on round T, you select your action xt, typically via some update steps, for example, SGD, and then the environment reveals the loss function ft. And what I'm actually going to assume, I'm just going to assume that ft is convex for each t, and ft is revealed after the action xt is chosen. Okay, all right. So now I want to evaluate how well my algorithm, the underlying algorithm that I am actually using for updating these weights, this is actually working. So I'm going to evaluate the benchmark my model. So I'm going to compare the performance of my algorithm against a fixed action in hindsight, right? And this is a fixed action in hindsight. This cannot be computed a priori. This can only be computed after you have seen all the examples. That's of all t examples. And what it means? It means that you pick a single action xstar, that's the optimal set of weights for your neural network, that minimizes a cumulative loss function for all t rounds. That is for all t data points. There is a single action extract that minimizes cumulative loss, right? And I'm going to evaluate the performance of my algorithm with respect to this single action in hindsight. All right. And how am I actually going to measure this performance? I'm going to measure this performance with a metric called regret. And how is a regret metric defined? So it is a difference between two terms. The first term is the cumulative loss of your algorithm. So this is ft of xt, the sum of all the losses that your model suffers for these t data points, and the second term being the loss of the benchmark, that is ft of x star. So this is a cumulative loss of this the best benchmark in hindsight. And I'm looking at the difference. So of course, you would like to minimize the loss of your the model's loss, which means that you would like to minimize the regret, right? So the question is, how do you actually design an algorithm that minimizes the regret? And typically, theoretically, what we would like to show, we'd like to show that this regret grows sublinearly in time. That is the number of data points, which means that if you divide this thing by t and let t go to infinity, t is very large. If it goes to 0, this means that you are actually learning. You are actually learning the best action in hindsight in terms of the loss function. Yeah. Yeah.
Might not seem direct, but shouldn't ft xt be the not just a single, like every step you are choosing that action which is minimizing, shouldn't that be the ideal benchmark?
Yes, very good question. Now, what is the ideal benchmark is that, so do you want to choose your ut, let's call it ut, after seeing ft, the art meaning of that. So this benchmark, this is something that I'm going to cover tomorrow, not today. So this is called the dynamic regret metric, and it is kind of much more difficult to optimize. But so this is called the static regret metric. But this is the focus of this talk. Tomorrow we will be actually doing the same benchmark that is called the dynamic regret metric, where this xt can also x star t that can also vary with time, arbitrarily with time. Right? I'm going to talk about it. All right. Okay. So now. So you see the static regret metric, and now you might say, okay, so you're revealing these functions, the loss functions, after seeing the action. And I'm not giving you any mechanism how these functions are revealed or how functions are chosen. This could be chosen by an adversary who could see the action xt that you have just revealed and then give you some function ft which does pretty worse performance, on this particular action xt, right? So maybe there is no hope of getting a sublinear regret bound, anything that is non-trivial. But the key thing to understand is that you can change your action xt on every round, but the benchmark remains fixed. So this is a limitation of the benchmark. The benchmark, of course, has a benefit of the hindsight, but it cannot change its action. But your algorithm can, of course, it doesn't have the benefit of hindsight, but it can change its action. It can learn its action on every round. So by exploiting this, it turns out that indeed we can actually design an algorithm which has sublinear, which has non-trivial guarantee, order of root t regret is actually achievable, and this is also tight. At least in this model, In this convex model, no algorithm can do better than order of square root degree. And what kind of algorithms achieve this? Not surprise, there is no surprise here, online gradient descent. And online gradient descent means nothing but stochastic gradient descent. These are the same algorithm. Why you call it online? Because we just underlying assumption is different, right? And what does online gradient descent does? It just looks at the previous action xt minus 1 and takes a gradient step on the last action, loss function that you see, right? So let's say I'm at round t, and this is a function ft that I ideally would like to minimize, but I have not seen this function ft. What I have got is the last function that is ft minus 1 and the last action xt minus 1. So what does online gradient descent do? It simply takes a gradient step on ft minus 1 towards the minimizer of ft minus 1 of the step size eta t. I'm going to talk about the step sizes later. This is important, but right now, so you can assume that eta t is something like varies like 1 over root t, right? And you get xt, and for let's say I just choose my step size as proportional to 1 over root t, and turns out that this simple algorithm, online gradient descent to the 1 over square root step size, it achieves the minimax optimal order of root t static regret guarantee. So pretty standard. So this has been studied for more than 30 years, and this is like very initial early results. Okay, so the modern paradigm. So this is a learning with constraints. So what we see in modern machine learning is that there is always a single objective function that you're trying to optimize, right? I mean, there are very little work in machine learning that is actually trying to optimize two different objective functions, multi-objective functions, because these problems are very different and very difficult, right? So but these problems are also important from a practical point of view. So modern applications are most of it not, they are multi-objective in fashion, and we also need to satisfy the constraints. For example, one type of multi-object optimization problem is that in addition to the cost function, let's say you also have constant functions, and you would like to minimize the cost function, subject to that you satisfy the constant function. But similar to the cost function, you also don't know the constant functions a priori. So how are you going to satisfy the constraints, unknown constraints? And in addition to that, you would also like to minimize the objective function. So it is the difficulty is like twofold, right? But this is a practical problem. So for example, let's say you are you're working for Uber and you would like to do autonomous driving. And I don't know what is the current company that is doing the autonomous driving in the US. Huh? Honda? No, I mean the US there are some other companies, I think. Yeah. So let's say you're an engineer woman, and what you want to do, you would like to design an RL algorithm or something like that, that would like to, let's say, autonomous driving algorithm, right? But your objective might be to get from point A to point B in the shortest possible time, but you can't just blitz through the road, right? You have to satisfy certain constraints. Maybe some pedestrian is actually crossing the road at some point of time, and you have to respect that. I mean, you can't just hit him and just go, right? So you have to make sure that you don't hit the pedestrians. You also have to make sure that you maintain sufficient distance with other vehicles on the road, safe distances, and you also have to satisfy at least. I mean, it doesn't apply that much in India, but in the US, you have to satisfy the traffic constraints. So you have to the traffic signal. But in India, this is also fine. So, but anyway, the important point to remember is that these constraints are not fixed. These constraints are only revealed on the go, right? So when you leave for the office, you don't know which pedestrian is going to cross the road. So you're on the road, you are seeing, and then this pedestrian is crossing, then you have to stop, right? So these constraints are on the revealed on the go, and they also cannot be modeled like simply sampled from some IID distribution. These are adversarial, much more like adversarial setting, right? So you have to learn these constraints. So you have to actually act online. Right. So the question is, okay, how do you actually solve this sort of problems? That is a constant. So it is a multi-objective when you have got, this is two versions of this problem. So here you have the constant functions. You have got two functions, f and g, and I would like to minimize this f subject to g is smaller than some given constant, right? This is a safety constant. In multi-objective, you have got two functions, let's say f1 and f2. These two problems are related, and you would like to achieve some Pareto optimal frontier on this f1 and f2. So I'll not be talking about the multi-objective problem in this talk, but I'll be talking about something similar to this, a constant optimization problem that we actually understand. But these problems are similar in spirit. Yeah. G1, G2 online, and they're also adversarially generated. Okay, so actually, I mean, there is a very little distinction between these two, right? Because GTs are adversarially generated. Now the GTs could be parameterized, and this parameter could be adversarial. You can say that these parameters are adversarially generated, but I am not going to tell you how these GTs are generated. GTs are generally adversarial. Yeah, I'm just going to assume yes, GTs are going to be very widely different from each other.
Then what are
Right. You're absolutely right, and I'm going to talk about this. So here we are definitely going to make some assumptions, and I'm going to gradually relax these assumptions. In today's talk, I'll be doing a kind of much more stronger assumption, right? We will call it common feasibility assumption. We are going to talk about that, but just in 5 minutes, we'll tell you about that. The next talk, I'll be doing a much more general model. All right, but of course, so GT needs to be has to have some sort of sanity. I mean, we can't do absolutely arbitrary things. All right. Okay, any question? Any more questions on that? Okay, so the constant learning, so lots of applications, so especially in the domain. So this constant represent undesirable side effects from some, it could be like AI safety, generating harmful content, or let's say this is smart grids, and you would like to have some control on the emissions, that harmful emissions. It could also be budget constraints. For example, bandit with knapsack, it's a very well explored problem in the bandit literature. So auto bidding is with limited budget is an application for that. So Google, for example, companies like Google, they are very interested in this. Meta learning or multitask learning, what happens is that you train a foundation model, and then you use this foundation model for many downstream tasks. Now these tasks are kind of related, and you would like to do well in all of this. So it is kind of a multi-objective fashion, multi-objective problem. And similarly, the wireless network traditional applications, where you would like to maximize system utility subject to all users get treated fairly, right? But all of these problems can be modeled in this general framework that I'm going to describe. Okay. So now, okay, so I already formalized the online convex optimization. Now let me formalize the constrained online convex optimization, which you call it COCO. Okay. So here you similar to online convex optimization, you've got multiple rounds. So let's say you've got T rounds. On round 1, you first choose an action x1, and then the adversary or the environment reveals two things. The first is the cost function, which is actually common in the online convex optimization as well, and it also reveals a constant function. Let's call it G1, right? And G1 is another arbitrary convex function, and G1 can depend on x1, right? Sorry? Yeah. So this is without any loss of generality, because even if you have got multiple constants, you just take a max of this, and you can just reduce it to a single constant. So it's a multi-dimensional constant also, yeah, you can also treat it. So what happens is that, so you have selected the action x1. So as a result of this, you incur a loss of f1 of x1, and you also incur a constant violation of max of 0 g1 of x1. And why max of 0 g1 of x1? Because assume that your x1 already satisfies a constant, then you are fine, you are not violating the constant, it is, your violation is 0. But if your g1 of x1 is actually positive, then you actually incur a constant violation of the order of g1 of x1. Now this game continues for T rounds. For example, on round T, you select an action xt, then the adversary reveals you these two things, ft and gt, and you also incur a cost of ft of xt and constant violation of max of 0 gt of xt, right? And my standing assumption is that ft's and gt's are convex, and ft's and gt's are revealed only after action xt is chosen, and this could be chosen in an adversarial fashion. So what I would like to do, so here is the assumption, at least for this talk, that I'm going to make. So here, similar to the online convex optimization, I'm going to compare the performance of my algorithm against a single benchmark. Let's call it x-star. So this benchmark is something that minimizes the cumulative loss function, subject to the fact that same benchmark x-star satisfies all the constants. gt of x-star is less than or equal to 0 for all time t. Right? This particular assumption is known as a common feasibility assumption. So actually, people actually make even more stronger assumption. This is called Slater's condition, but this is the kind of less strict assumption. This is a common feasibility assumption, but I believe that it is also it is also kind of very strict. But it simply means that star that satisfies all the constants, right? So this is how this x star, these constants are related among each other. Because if they are totally arbitrary, then there is no way you can actually do anything. You can say anything in this model. But in the tomorrow's talk, I'm going to even relax this assumption and we'll see how far we can actually go. So this I don't know why it's not working. Huh? Okay, I see. Okay, so all right. So as I just said, so we can drop the common feasibility assumptions. This is the little basis of my tomorrow's talk. Okay, so what we have got? So let's say S is a set of all convex. This is a convex set. There is the intersection of all these GT of X. So it is S is itself is a convex set, and I would like to find an action X star. So we are going to assume that S is non-empty because my X star, my benchmark, lives in S. And generally, it actually holds in over-parameterized neural network where your number of dimension is much larger than the number of data points, right? So you can actually, this interpolation. It is an interpolation regime, right? So again, so in summary, so what we are actually going to do, we are going to consider this benchmark argmean of X, sum of ft of X, where this argmean lies in this set S. And that is ft of xt minus ft of x star that I also defined in the setting of online convergence optimization. So this will be like my first metric, but this only captures the suboptimality with respect to the cost function. And I'm also interested in the constant violation, that is cumulative constant violation, that is a max of 0 gt of xt. So what I would like to do, I would like to simultaneously control these two metrics together. So I would design an algorithm such that both of these two quantities grows in a sublinear fashion. Okay, any question on that? Yes.
That a lot like that negative GPXT is not going to compensate for
no. So you have to. It is not like there are, let's say, 2 pedestrians or maybe 100 pedestrians. Maybe in the budget setting it makes sense, but you have to satisfy the constant, all the constraints. So it is not like since you just avoided the first 99 pedestrian, you can hit the last one. You have to make sure that you are safe all the time. So this also got this has got a name. It's called the hard constant satisfaction. So people actually looked into both the versions. So I'm going to talk about these things when I describe this in this slide itself. So okay, so we would like to control these two things together. And so of course, so this is an interesting problem, and many people have actually looked into this problem before. And here are some guarantees. So this is called the soft constant. So what you just said is called the soft constant violation, which means you can compensate. So only you are trying to control the sum of gt of xt without this max, right? So this is called the soft constant violation regime. This is a slightly easier problem. And then soon et al. 2017, they had an algorithm that has a square root regret and t to the power 3/4 soft constant violation. Then Neely and Yu, they actually assume something called the Slater's condition. Slater's condition means that not only the common feasibility, but gt of x is less than equal to minus lambda for some strictly positive lambda. Right? It is a even more stricter assumption. It doesn't hold in most of the practice, in the applications that we actually care about. Sorry? So gt of x star is less than equal to minus lambda. So there is a benchmark. So it says that there is a benchmark that has strictly negative, not the penalty. I mean, the penalty means the constant function. GT of xt, yes, but yeah. No. So even tomorrow, okay, so tomorrow's talk again, I'll just drop this assumption of common feasibility. Yes. Yeah, then it becomes kind of similar to the cost function, right? Because in the cost function, I'm only looking at ft of xt minus ft of x star. But in GT, this is the constant. So the difference between the cost and constant is that cost you would like to minimize, constant you would like to satisfy. So you have to make a distinction between these two.
Like, people is like, does it even people
No, it doesn't give. Okay, from an application point of view, it doesn't mean that. It doesn't give you anything, right? It just, but it means that theoretically speaking, it says that there exists because you don't know extra. Algorithm doesn't use the knowledge of extra. It is only used for theoretical purposes for proving the regret and the violation bounds. Yeah. Yeah. Yeah.
You need to have sort of a period point, or does the optimal need to be?
For which, in our setting,
Feasibility.
it just has to be feasible. That's it. I don't need any interior point, but they do need that. So Neely and you, the previous work, they need something called Slater's addition. So this is the Slater's condition. Okay, all right. Moving on. So now in 2022, so this is the first algorithm that doesn't assume any Slater's condition or any other strange things, and it gives me a very clean bound, regret of square root t, and violation of order of t to the power 3 by 4. This is in the same setting as ours. This is a hard constant setting. So the problem was, and also this algorithm was actually extended, generalized. So they had E et al. In 2023. They had an algorithm that kind of generalizes the regret bound. So t to the power max of beta and 1 minus beta, and violation of t to the power 1 minus beta by 2. But if you would like to get to the optimal regret bound, that is square root of t, you have to set beta equal to half, and that means the violation of t to the power 3 by 4, no better than Go et al. Right. So the open problem that was there for the COCO problem, just this assumption. What is the optimal bounds that you can get simultaneously for regret and CCV? So for example, is it possible to simultaneously achieve square root t regret and square root t CCV unconditionally? Right. So this is our result in 2084 new reps. So we prove that there is a very simple algorithm. I'm going to describe the algorithm, and it achieves square root t regret and square root t CCV unconditionally in this setting. Okay, and also it is tight. You can't do better than unless you make additional assumptions. Okay, so this result is actually surprising because previously it was conjectured in ISML 2019 paper that this result, like square root of regret and square root of CCV, is impossible to get unless you make some additional assumption. For example, without the Slater's condition assumption or any other assumption, this result is actually not achievable. So we actually prove that. So yeah, I'm just quoting the one line from their paper, but we disprove this conjecture with a very elegant algorithm that I'm going to describe. Okay, so this is the template of our algorithm, how our algorithm works. So we make a black box reduction. Okay, so we are going to reduce this COCO problem to an instance of the OCO problem, right? We are going to design kind of surrogate cost function, right? And we'll be running a simple and standard OCO algorithm on the surrogate cost, and we'll be deriving bounds for both regret and CCV from this by analyzing the surrogate costs. Okay, so it is a simple, cleaner and modular algorithm yielding optimal bounds, and it replaces the previous primal dual based and suboptimal algorithms. Okay. So all right. So now the whole question boils down how we are going to design the surrogate cost functions, right? And so let's denote it by f hat of t. And so how do you actually combine this cost and constant functions? How do you define the surrogate cost? So here is a very simple idea. Can I just add this together and run an OCO algorithm? This is maybe the first idea that comes to your mind, and we'll see that it actually doesn't work. And the important thing is to realize is why it doesn't work, and then it will give a point as to the actual algorithm that will make it work. Okay. And not only it doesn't work even when the functions are time invariant. They are not changing, and we are just solving a classical optimization problem. The mean of f subject to g of x less than equal to 0. So here is a simple counter example. Let's say I have got a decision set. My decision set is simply the closed interval -1, 1, and consider this time invariant cost function ft of x to be the quadratic x minus half whole square, and the constant function to be linear. That is, let's say 0.2 of x. Right, for all t greater than equal to 1. So nothing is changing with time. This is a very simple time invariant classical optimization problem. So now let's see if we just design a surrogate cost which is simply fx of gx and run any online learning algorithm, let's say online gradient set, then what happens? So what is the minimizer of fx? Minimizer of fx is strictly lying at 0.5, of course, and the decision set is -1 to 1, and the feasible set where g of x is less than equal to 0 is simply the negative half, right? The negative half, there is a minus 1 to 0. And what happens now? This is my fx plus gx. So now let me just construct this function. So this is fx plus gx, and where does the minimum of this function lie? So it is actually, if you just do this calculus, it is 2 by 5, 0.4. Now what will happen if you run any online convex optimization algorithm on this fx plus gx? If it is it is a good algorithm, it is going to concentrate on the minimum, right? That is 0.4. And if it the iterates going to convert to 0.4, so here it is okay. So here it is a feasible set, and it is going to convert to 0.4. Now if it is the iterates are going to convert to 0.4, what happens to the constant violation? It increases linearly with time, right? So you have got CCV is going to be linear in time. Of course, I mean, it happens. So the fx plus gx doesn't work. So how can I actually make it work? Okay, so this gives you, so why it actually doesn't work? It doesn't work because the constant, right? So in other words, so if you knew the constant functions before, what you could do, you could just add a one Lagrange multiplier, properly chosen Lagrange multiplier, and we just solve this using some online gradient descent, then it would have definitely worked, right? So, but in online learning, we simply do not know this function FTs and GTs a priori. So there is no way of computing this Lagrange multiplier, right? So what you actually want, we want something like ft plus wt times gt, where wt is a Lagrange multiplier. This should be, it should not be bold, should be simply a scalar function. The idea is, how do you actually learn this multiplier, right? So if you could learn this multiplier on the go, then this algorithm will work. So this surrogate cost, which is simply the sum of two this different thing, this is qt minus 1 plus gt of xt plus, right? So this is your constant violation. And now this is how I'm actually going to define my wt. Wt is simply going to be phi dash of qt. So I'm going to talk about what this phi is. Phi is a very simple function. It is going to be an exponential function, but I'm going to talk about that later. So, but the important point to remember is that it is a time varying CCV dependent, that is a violation dependent weighting factor, right? I'm going to again discuss like how this how I'm actually deriving this sort of expression for these weights. This will be clear in just a second. So phi is a convex Lyapunov function, and we now consider simply fit this to some online convex optimization subroutine. For example, online gradient descent, right? But there is a small catch. The small catch is that in online gradient descent, you generally assume that you have an upper bound to the Lipschitz constants of all the FTs. But here in phi dash of qt, the Lipschitz constant is dominated by this phi dash of qt, and a priori I do not have an upper bound to that. So I need, so of course I'm going to feed this to some OCS subroutine, but this OCS subroutine should be able to handle Lipschitz constant. So this should be Lipschitz adaptive, which means it should not need an a priori upper bound to the Lipschitz constants of all the cost functions. But these algorithms are well known. For example, ADAGRAD is one of them, right? So what I'm actually going to do, I'm just going to construct this surrogate cost function, and I'm just going to plug this surrogate cost to this ADAGRAD subroutine, and this is how I'm actually going to generate my XTs, my actions. So this is a simple algorithm. Any question on this design?
Phi is a family.
Phi is not a family. Phi is just a simple function. We'll see what this function is. Phi is right now, you can just assume to be a non-decreasing. It's a scalar function. Phi can be any convex Lyapunov function, and here phi is going to be simply an exponential function. Okay, but we will also be able to derive the exact form of phi that gives you the optimal bounds. It will be clear. So the choice of phi is non-trivial. If you use, for example, square function, it is not going to work. It is not going to give you the optimal bound. You have to choose something else, and what you have to choose, it will be clear from the analysis. It will give you 3-line analysis. It will be clear from this. Okay. No. What do you mean? So you said that. So assume that I know that. So I have already fixed my form of phi, or I'm going to use ADAGRAD algorithm. I'm going to use attack-led algorithm, then the algorithm itself will tell you what phi to choose. Yes, yes, it will be implicit. It will not be explicit, but it will be implicitly. We will see that. It will be just clear in a second. Yeah.
That part as like the process.
So first of all, phi is just it is a defined on the real number. It is not. Its domain is not x. I'm not very sure of that. Yeah, QT. So CCV. It is a CCV up to round t. Yeah. Okay, the form of phi will be clear. So how do you actually design the optimal function phi? Okay, so our algorithms, we have already discussed this. So the analysis, again, the analysis, I understand this is like the first talk, so it should not be very heavy. And indeed, the analysis is actually 3 lines, so I'm going to include it here. So, okay, so the algorithm is the first to have computed my violation so far, and this is my surrogate cost function that I have already discussed. And here the analysis starts. The convexity of phi gives me the first order Taylor series bound, right? And qt minus 1 by this, the way this qt evolves, it is simply going to be gt of xt plus, right? So phi of qt minus 1. So this is how the potential function changes. So think of phi as a Lyapunov function and potential function, and the change in potential function can be upper bounded by this quantity phi dash of qt gt of xt plus. So this is how this multiplier is actually entering into this picture. And now what happens is that now you recall the feasibility assumption. The feasibility assumption is very important. Feasibility assumption says that your optimal, or not the optimal, but the benchmark satisfies all the constants, all the t constants, which means that x star, although I don't know what this x star is, but this gt of x star plus is going to be equal to 0. This is going to be my benchmark, right? Okay, all right. So let's now plug this in. So I've already got this thing, this from this simple upper bound on the change in the Lyapunov function. And now I just add this 0, this gt of x star 0 to this. And next, I need to factor in the cost functions as well. So let me add the ft of xt minus ft of x star to both sides, right? And sum this up. Sum up from telescope, and this is the inequality that I get. Everything is algebraic, and it can be done with high school level algebra, right?